Let us move on from studying basic functions and now have a look at differentiation of functions. Differentiation is a mathematical procedure which describes how functions change. This is really important for physics because physics is really at some level the subject of how things change. So if we talk about dynamics, we're talking about velocity and acceleration. These are all to do with how things change. The acceleration of an object is a change in velocity and so on. Mathematically, we think of derivatives as producing something called a tangent to a curve at a point, and these concepts are essentially the same thing. Let's have a look. So we begin by just looking at tangent lines of functions. So what's a tangent line? Well, a tangent line at a point on a function is a line which has the same gradient. Why do we do this? Well, if we take an example of a function, here's an arbitrary example of a function, sine x plus a half x. You can see it's a fairly wobbly function that increases with x in either direction. But if we zoom into the function, if we zoom into a point here, we can see that it starts to straighten out a bit. And if we zoom in further, and further, and further, and if we do this infinitely far, we end up with something which is exactly a straight line at a point. This straight line has a slope. This is a concept of finding the derivative of a curve at a point. We can zoom in and it becomes a straight line, essentially. So how do we go about calculating what that might be? Well, let's just review the basic concept of the picture. So let's take a curve and let's try and find the gradient of the curve at this point here. Now at this point, the function has a slope which is the same as this line. And let's say the slope of this line is m. Now what we want to do is take in a point nearby this point, x equals a, and slowly move the function towards that. So let's take another point. Let's say this is f at the point x. And the idea is that we're going to move x towards a using the concept of limits. The function height at this point is f of a. And so if this function is y equals f of x, change in height here, which I can write as delta y, this is just f of x minus f of a. And this distance along the x direction is just x minus a, and I'll call that delta x. Now the idea of derivatives is that if I make delta x small, then I move this point towards our target point, x equals a. So I reduce delta x and I slide x along towards a, and at the same time I decrease the height of the function. So mathematically, we can say that as delta x goes to 0, delta y is also going to 0. But crucially, the ratio of those two things is tending towards a constant. And this constant is the slope of the tangent line at x equals a. So this is just equal to m. So mathematically we write this as the limit is delta x tends to 0 of delta y over delta x. This is equal to then the limit x tends to a of f of x minus f of a divided by x minus a. Or alternatively, we can just write this as the limit as delta x approaches 0 of f of a plus delta x minus f of a divided by delta x. Both of these are valid descriptions of a derivative. Let's have another motivational example for how we might come across a derivative. Instead of looking at curves, let's consider velocities. If we consider velocities, we're considering rates of change of objects. So for example, if an object is moving, its displacement over time is changing, and the change in that displacement over time is the velocity. So let's write the displacement as x, and this is a function of time. As time evolves, so does the displacement. Now, the average velocity over an interval delta t is just the change in the distance over the time. So that average velocity is just the change in distance over time. Now this is equal to x at the end of the time period, which is x of t plus delta t, minus x at the initial time, divided by the time period, which is just delta t. Now if we think about travelling on a train, for example, the time period might be a few seconds, a minute or so, something like that. The average velocity over that time period isn't going to change very much. And as we let that increment of time get smaller and smaller, so from seconds to microseconds to nanoseconds and so on, we come up with the concept of instantaneous velocity. And instantaneous velocity is when we take the limit formally as delta t goes to 0. So the instantaneous velocity is itself a function of time, and it's the limit as we take the average velocity over a shorter and shorter time period. Mathematically, that is in the limit when delta t tends to 0 of the difference between the displacement at one time interval minus the displacement at another time interval separated by delta t. So what we've seen here then is that slopes of curves over an infinitesimal range and the instantaneous changes of functions in time require derivatives of functions. So we define the derivative of the function y equals f of x is another function which we denote with a prime on the f in here. And that other function is the limit as h tends to 0 of f of x plus h minus f of x all over h. There are different ways to write this limit, so you'll often see this as the limit as z tends to x of f of z minus f of x divided by z minus x. And this is the same definition on using the fact that we can let h equal z minus x. We can also write, which is where we came into this, as the limit as delta x goes to 0 of the ratio delta y over delta x. And in fact, this gives the more suggestive notation that we can write the derivative as dy by dx.